So let's continue talking about transformations of the basic functions. Remember that you do have quizzes due this week and a test coming up. Check your course outline for the date and time of your test. We want to look now at vertical stretches and compressions. And again, we're going to use the quadratic function graph as our basic graph. So you have the points that you've memorized here. And this is going to give us our basic x and y. And maybe let's even throw in there a couple other points just so we can use them as comparison when we do our stretch. We know when x is 2, y is 4. When x is half, y is 1 by 4. And we can, of course, use symmetry. We know that our quadratic function is an even function graph. It's going to reflect across the y-axis. So I have a point here, here, and here, giving us our basic function. So now we want to change the multiplier, the coefficient. When we're looking at our basic function graph, we know that we're multiplying our basic function by a equals 1. And if you look at the next two examples at the bottom there, you can see that we've changed the value of a. We're starting with a equals 2. So are we changing x or are we changing y? Remember, function notation tells us that the f of x represents y, and y equals x squared. So here's our x squared. This is y. We're changing y. If we were changing x, then 2 would have to be inside the function. It would be squared with y. This gives us a value that changes x, not y. Let's get rid of that. So we know that our x values are staying the same, and it's 2 times y. X is the same, 2 times y. X is the same, 2 times y. X is the same, 2 times y. Let's graph these points and see what this looks like. We had a point at 0, 0, 1 half, 1 half, 1, 2, 2, 8. And using the symmetry of this function, we can graph our parabola. Now, if you look at that in comparison to our basic function, you can see that it looks taller, thinner. We say that this graph has been vertically stretched. And this makes sense. When you multiply a number by another number greater than 1, you're going to have faster growth. In our next example, we're multiplying y by 1 half. X is staying the same. 1 half times y. Now remember, these are our y values over here in the first column. In the second column, it's 2 times y. We want a half of y. X is the same, a half of y. My eraser doesn't work very well. I hope yours works better than mine does. X stays the same, a half of y. X stays the same, 1 half of y. X stays the same, 1 half of y. So and using symmetry, when we compare this graph to our basic function, we see that it is wider and it looks shorter. This graph has been vertically compressed. So, given our basic function, but now we have some coefficient a. When the function is multiplied by the absolute value of a greater than 1, we know that this graph is going to be vertically stretched. But when the absolute value of a is a fraction between 0 and 1, then we have a function that will be vertically compressed. And remember that a is multiplying our y values. And I'm not going to say the absolute value of a. We're just going to say that we're going to multiply our y by a, whatever it is, so that if we have a negative a, then we know we have a reflection across the x-axis. So a reminder when we are graphing that we always start with the basic function and then we apply any reflections, stretches, or compressions. So let's look at this example. We see that our basic function is x squared, and that gives us those key points that you've memorized. If you haven't memorized the basic function points from our introduction to those graphs, make sure you do so. It will make graphing these functions much easier. Now we have this negative sign. It is a negative of x squared. X squared is our y. So x is staying the same, and we have the negative of y. X is staying the same, the negative of y. X is the same, the negative of y. X is the same, the negative of y. Remember, this is a reflection. What kind of reflection? Across the x-axis. And then we have the transformation of that plus 3. What is the plus 3 going to do to our graph? Is it changing x or y? It's outside of the x squared. It is changing y. X is staying the same. We still have negative y. That means we're using these values for y. And then we add 3. X is the same, negative 1 plus 3. X is the same, 0 plus 3. X is the same, negative 1 plus 3. So let's put in our x and our y axis. Make sure you label them. negative 1, 2, 0, 3, 1, 2. We knew, of course, that that plus 3 was a vertical shift up 3 units. And there's our graph, reflected across the x-axis, shifted up 3 units. Pause the video. You see I've written the first 2 in here that you need to find. See if you can find all of your points for the new transformations, and then try graphing it before you start again. Do you know what this graph looks like? Our absolute value function. Have you got these key points memorized? Remember, this is A. It's our reflection and a stretch. X is staying the same. We're multiplying A times Y. X is staying the same times negative 2. X is staying the same times negative 2. X is staying the same times negative 2. Now it doesn't matter whether we do the plus 1 or the subtract 3. I like to work with whatever is closest to X first. Absolute value of X plus 1. Are we changing X or Y this time? Well, the plus 1 is inside the function with X. That means we're changing X. And remember, when we're doing those horizontal shifts, you're going to do the opposite to X. We still have our negative 2Y. That means those values of Y stay the same. But we have to add 1, we have to subtract 1 from X. Negative 1 minus 1, 0 minus 1, 1 minus 1. Remember that if you're not sure, you can check your ordered pairs. What if we substitute a 0 in here? 0 plus 1 is 1. The absolute value of 1 is 1 times negative 2 gives us negative 2. Our final transformation then is that subtract 3. This time we're changing Y. Now we still have our X minus 1. So those values for X minus 1 we're keeping. We still have that negative 2 times Y. And now we have to add 3. We're adding 3 to these values. Negative 2 plus 3, 0 plus 3, negative 2 plus 3. And again, we can check. Let's check this ordered pair. If we substitute negative 1 for X, negative 1 plus 1 is 0. The absolute value is 0 times negative 2 is 0 plus 3 gives us our 3 there. So we have the correct ordered pairs. Now we just need to draw in our X and our Y axis. And just a reminder to label your axes. I think especially in a calculus class, oops, your professor is going to be looking for that. Maybe I'll make this a bit smaller so I can see everything. Why is it drawing? There we go. Give me a moment. My pencil's being a bit weird. So there's our absolute value function reflected across the x-axis, shifted 1 unit to the left and 3 units up. If you haven't found the domain and range already, please pause the video and give that a try. We can see that this graph is continuing infinitely left and infinitely right. The domain is the set of all real numbers. And it's clear that this graph is moving down all the way to negative infinity, but it has a highest point at y equals 3. And of course, we would use a closed bracket there. So again, why don't you pause the video, see if you can do this one. Remember, you're going to start with your basic function, and then next, any stretches or compressions. The basic function is, of course, our square root function. This is giving us our x and y values, and you've memorized those key points. And then we do have a compression. We're multiplying our entire function by 1/2. This is changing our y values. X stays the same, 1/2 times y. I like to work with whatever is closest to x next. Again, remember, this is going to be a horizontal shift. And when we're doing a horizontal shift, we're always doing the opposite to x. This is going to be x plus 3. We're keeping that 1/2 y. X plus 3, keeping the 1/2 y. X plus 3, keeping the 1/2 y. X plus 3, keeping the 1/2 y. And finally, we have that plus 1 outside of the function. That means it's going to be a vertical shift up. That means we're changing our y values. We're keeping those x plus 3. And now it's a 1/2 y plus 1. And can I remind you again, I haven't said that this lecture, that when I find people making mistakes, it's because they haven't bothered to write this out. Unless you already knew how to do these transformations before you came to this course, I would strongly suggest you write out these small formulas that help you find your new ordered pairs. Now, you've probably noticed from time to time I have to pause the recording. I don't know why Word stops responding, but rather than make you wait while it cycles through, I'm just going to pause, let my computer do its thing, and come back when everything is working again. So we're keeping our 1/2 y plus 1 and our 1/2 y plus 1. And remember again, you can check your ordered pairs. If I'm not sure about them, I can let x equal 7, substitute it in here. 7 minus 3 is 4. The square root of 4 is 2. 1/2 of 2 is 1. Plus 1 is 2. So we have our new ordered pairs. Let's make this a bit smaller again. Draw in our x and our y axis. So we have a point at 3, 4, 1.5, 7, 2. And our graph looks like this. If you haven't found the domain and range already, pause the video and try writing it in yourself. Don't just think about it. People always think and then they say, oh yeah, that's what I was thinking. Maybe not. It's better to write it down. We see that our lowest point on the x-axis is here at 3, and then the graph continues to the right to positive infinity. Our lowest point on the graph is at y equals 1, and then continuing up to positive infinity. One final graph for you to try in this lecture. Pause the video, give it a try. So our basic function here is our rational function or our reciprocal function. And I hope you remember there were only 2 key points for this function. Oops, that's a -1. But I suggested that you fill in your vertical asymptote and your horizontal asymptote here as well. If you didn't do so, do it now and make sure you find your asymptotes for the final graph. And then I've suggested that you start with any reflections, stretches, or compressions. We have this negative sign. It is outside the function. That means it is changing y. X stays the same, the opposite of y. X stays the same, the opposite of y. But of course, the opposite of 0 is still 0. And I always like to work with the numbers closest to x first, but you could do the +2 if you like. This -4 is inside the function. It is changing x horizontally. And for a horizontal shift, we do the opposite. We're keeping that -y. Add 4, keep the -y. Add 4, keep the -y. X, add 4, keep the -y. So many colors. And finally, we have that +2. It is outside the function. It is changing y. We are keeping all of these x plus 4 x plus 4 values, and we're going to take that -y and add 2. Here's our -y, add 2. Our -y, add 2. Our -y, add 2. Can you see why it's important that we wrote in our asymptotes here? They had to move as well. So let's put those asymptotes in first. I always think that's the best place to start. So we had an asymptote at x equals 4. We use a broken line for that. You label it. We have an asymptote at y equals 2. Make sure you label it. And then we have a point at 5, 1. And a point at 3, 3. And there we have our reflection across the x-axis, moved 4 units to the right and 2 units up. We see that the domain continues on the left to negative infinity all the way up to 4, jumps over 4, and continues to positive infinity. The range is going down to negative infinity all the way up to 2, jumps over 2, and continues to positive infinity. Now I wanted to do a quick review of some of these properties using our reflections. Can you do a quick sketch of x squared, negative x squared, and the negative x all squared? You remember that the negative outside the function is the negative of our y values. A reflection across the x-axis. But when the negative is inside the function, it's a reflection across the y-axis. And we notice that the f of x gives us f as the f of negative x. The quadratic function is an even function. That should make sense to you because, of course, when negative x in brackets is squared, it equals positive x squared. So what about our cube root function graph? You know these key points. The negative outside means it's a reflection across the x-axis. The negative inside means it was a reflection across the y-axis. And we notice that the negative f of x equals the f of negative x. That reminds us that the cube root function is an odd function. Finally, we have our square root function here, our basic function, our reflection across the x-axis, and our reflection across the y-axis. None of these are the same. The square root function is neither odd nor even. The graphs let us see those properties pretty clearly. Now you're going to want to remember these definitions for odd and even functions because we will talk about them again when we get to trigonometry, and I will expect that you remember this definition. I want to close this lecture by asking you to take a look at this set of study notes. These are for you to fill in, so you can put all of the transformations in one place and memorize them for your test and your final exam.